Hello everyone, I'm Qiyu Chen from Tsinghua University. My major is lithium-ion battery modeling, simulation, and numerical solver development using OpenFOAM. I'm delighted to have the opportunity to exchange ideas today. The topic of my presentation is addressing the challenges in modeling heterogeneous battery porous electrolyte, causes and solutions. The context of this presentation is divided into the following 4 parts. First is battery design and electrochemical solver. First, let me introduce battery design and my solver. It is well known that good battery design can make the best use of the thermodynamic properties stored in materials. The traditional battery design is experimental trial and error method, including numerous sampling, testing, and selecting process, which is time-consuming and high cost. The new generation is the simulation design method based on the physical model, in detail input parameters, internal model, and final output of the battery performance. On the basis of ensuring accuracy, the efficiency is increased by 2 to 5 times, and the cost is reduced by 50%. The core of this method is model and numerical simulation. The essence of the model is a series of partial differential equations describing the internal geometric structures and the processing of the battery, such as mass and charge transfer, migration and diffusion, including the reaction. Our research group began to study a particle packing model considering solid-liquid phase separation of porous electrolyte. This model has numerous high-order and highly coupled partial differential equations and complex boundary conditions, which further increases the difficulty of numerical solution. We started the exploration of domestic electrochemical solver. So what is numerical solver? That is input parameters, internal grid drawing, space discretization, and numerically solving equations. Finally, output the performance of the battery, including time and space variations. The development of numerical solver is relatively difficult for the following 3 reasons. First, from a geometric point of view, a 2-dimensional region 100 thick and 1 microns long with heterogeneous phase requires nearly a million meshes and needs to adapt to the geometry. On the other hand, this set of equations has a characteristic of multi-physics field coupling properties, such as electrochemical field, thermal field, stress field, and stream, and more, in the form of high-order partial differential. Moreover, reasonable boundary conditions are needed to be set for numerical solution. There are a lot of interfaces in the model, and different interfaces, its boundary condition is different. The second part is mathematical characteristic of the battery. The electrolyte thickness is approximately in the range of 100 microns with differences of at least 3 orders of magnitude. Within this range, there are many geometric shapes with common conductive bundles having a scale of around 20 nanos. Agglomerate is around 200 nanos. Single crystal particle is about 2 microns, and graphite particle is 15 microns. The quality of the mesh determines the simulation results. For high accuracy, mesh refinement can be implemented, but this will also increase computational time. How to achieve accurate and efficient spectral discretization across multi-scales is the first sub-problem to consider. The next is spectral multiscale. In terms of time, the potential changes caused by electron conduction within the battery occur at megahertz frequencies, while lithium-ion transport frequencies are in the millihertz range, with a differences of 9 orders of magnitude. Time discretization involves the selection of time steps, iteration, convergence, and multi-scale issues. It is necessary to considering numerical stability, convergence, and finding a balance between accuracy and efficiency. For the time of temporal discretization, it is essential to consider the physical quantities themselves and the characteristic of equations. Taking the electrochemical model as an example, it can be broadly divided into transient diffusion equations and steady-state Laplace equations. Furthermore, it is necessary to consider the update frequency of physical quantities. Physical quantities can be categorized into instantaneous quantities with small time constants and its equation without time terms, and non-instantaneous quantities with long time constants and with time terms, such as concentration and temperature field. Consequently, a bench update frequency approach can be adopted, where transit quantities are iteratively updated with a quasi-steady state, and slow variables are updated progressively over time. Next is a characteristic 2, multi-domain coupling. The porous electrolyte contains a large number of physical domains and fields such as a potential field, concentration field, temperature field, and stress field. Different domains have different geometrical and physical properties, so its governing equations are different. How to deal with the effective coupling of different physical domains at the interfaces as well as the variable transferring is a major challenge in the development of electrochemical solver. Multi-domain coupling problems within the batteries can be broadly classified as the following. First, multi-domain mass transfer. For agglomerated structures, the concept of porosity is introduced. It's due to the assumption of homogeneous solid-liquid mixing, and when there is a difference in porosity between two neighboring physical domains, the problem of discontinuity of the physical field between the physical domains is caused at the boundaries due to the difference in physical properties. How to solve the equations in these domains as a whole is a major difficulty. Second is source term handling for equations. We know solving partial differential equations involves source term treatment, which differs for physical domains with different geometric properties. Third is composite flux continuity. The set of equations in our model is characterized by a high degree of coupling of multiple physical fields. For example, the equations describing the liquid phase current contain two physical quantities, the liquid phase potential and the liquid phase lithium-ion concentration, and thus the concept of composite flux exists. Since the inside of the cell is a closed system, the continuity and conservation of the composite flux needs to be considered at the interface, as well as the effect of the treatment on numerical stability on the convergence. Characteristic 3, efficiency. Traditional numerical solvers face the problem of high-dimensional expansion and dimensional catastrophe. For a one-dimensional homogeneous model, the structure is simple and the number of grids is small, so the matrix calculation is relatively simple. However, for the current two-dimensional non-homogeneous particle packing structure, a 100 microns thick and 1 microns long region requires nearly 1 million meshes, which is a large number, and it takes more time for both the mesh generation and the matrix computation. Continue to expand to higher dimensions, the mesh discretization is even more complex, and meanwhile, the complexity of the multiphysics field coupling relationships also exacerbates the computation efficient problems. To build we first analyze time-consuming aspects and find alternative. To build a neural network solver for batteries based on mathematical equations, we first analyzed the most time-consuming aspect of the traditional numerical solver is partial differential equation solving. Therefore, to improve efficiency, a suitable alternative must be found. Through research, we found a method where a single PDE is viewed as a generalized operator, which is then fitted using a small-scale neural network. Finally, these numerous networks are combined into a large network. Next are the challenges facing in developing numerical solvers for heterogeneous model and the corresponding solutions we have tried. Challenges 1. Differences in governing equations on the boundary conditions due to numerous interfaces and physical fields. The specific locations where this interface exists are not defined in the persuade two-dimensional model, and the interfacial electrochemical reactions are assumed to occur at all positions along the microscopic one-dimensional domain. Thus, it is understood that the set of equations for solid phase mass transport, liquid phase mass transport, and interfacial electrochemical reactions are all coupled and solved without distinction at every geometric position, which is to say, in a single set of control equations is shared globally. But this case is suitable in persuade two-dimensional model. However, for our heterogeneous model, the numerous active materials particles, which can reach tens of thousands in a typical simulation region, and the independent spiritual occupation by conductive bundles, which are considered part of the solid-liquid phase, result in a large number of interfaces. Determining the exact position of these interfaces is crucial. Additionally, there are differences in the control equations, source terms, and boundary conditions on either side of these interfaces. Challenges 2. The continuous smooth interconnected field spans multiple regions with different geometric parameters. Taking the liquid phase iron concentration equation as example, it is applied to physical domains with different transport parameters, such as the porosity differences. At the interfaces of adjacent regions, the liquid phase iron concentration Cl field is actually continuous, while considering the property epsilon Cl is discontinuous. While when solving the equations numerically, the matrix is discretized with the variable being epsilon Cl. Due to the differences in regions, it is impossible to construct a single sparse matrix for the entire domain. Hence, domain decomposition solutions we required. For the persuade two-dimensional model, we have adopted a domain decomposition iterative approach. First, the concentration Cl at the interface is obtained based on the flux continuity condition. Then the values are substituted into the equations for each side of the interface to account to considering the porosity, resulting in epsilon Cl. The entire model is divided into 3 regions, with equations solved separately for each region and boundary conditions defined independently for each interface. As shown in the figure, the interfaces are very simple. At the current collectors of the both anode and cathode, zero gradient boundary conditions are applied since there is no lithium-iron flux at these points. For the anode separator and separator cathode interfaces, one side is fixed a specific value boundary condition to ensure field continuity, while the other side has a fixed gradient to ensure the flux continuity. Since the concentration equation is a transient equation, the exact inflow and outflow rates cannot be determined at each moment. Thus, iteration is necessary to obtain the final self-consistent values. However, for the heterogeneous model, due to the numerous physical domains and complex interface types, domain decomposition iterative solutions are not suitable. So, we have tried a method to construct a coefficient transfer matrix based on the essence of discretization, transferring the porosity such as epsilon of from the position of unknown variables to the coefficients. This means moving it from the equation Ax equals B term to the A term in the linear equation. By doing so, we can solve the equations globally and avoid the issues associated with domain decomposition iterative solutions, and the time can be decreased. Challenge 3. Mass charge cross-domain coupling. We know Nernst-Planck equation describe lithium-iron transport in the liquid. The ion-trinket current in the electrolyte is influenced by both the electric potential field and concentration gradients. This complex flux resulting from the combined influences of two fields necessitate adherence to the continuity condition at interfaces, making a distinction from the flux continuity within a singular physical field. The current on the right-hand side of the equation represents the source term for the liquid phase current within the electrolyte. This equation is structured as a sum of two Laplace terms equals to a source term. During discretization, each term is discretized according to its corresponding physical quantity, yielding distinct sparse matrix. This transfer property is the phase center values at the interface, typically determined through interpolation between the two adjacent grid points. Consequently, the gradient phi L field is computed based on the cell centers of these grid points. This method assumes that the flux of Laplace terms on the boundary is continuous. However, as previously noted, the flux of an individual Laplace term is discontinuous. Rather, it is composite flux from both two Laplace terms that maintains continuity. This presents a contradiction between the discretization process and the actual physical phenomena. So, how to solve this problem? In the persuade two-dimensional model, we employ a method similar to that for the liquid phase lithium-iron concentration equation specifically. This equation is solved independently with each region. with distinct gradient boundary conditions and parameters such as defined separately to ensure the composite flux discontinuity. The final is the first part, conclusions and applications. This slide represents some important milestones in the development process of the solver. And this slide shows the electrochemical solver based on the Persuade two-dimensional model. It constructs a multi-physics coupling simulation framework, and the time evaluation and spectral distribution can obtain high precision. We compare our simulation of the OpenFOAM results with commercial software console under various operating conditions. We can see accuracy differences controlled within 18%, and some field can even below 1%. This is some output results from our electrochemical solver, such as solid phase and liquid phase ion concentration, solid phase and liquid phase current, potential field, and overpotential reaction current density field. Thank you. This is my presentation.
Thanks, Dr. Chen, for giving the nice talk. I think maybe we only have time for one or two questions.
Thank. First of all, are there any experiment we do compared to the solar result?
This slide.
This one is with the commercial code.
Commercial software console multiphysics.
Yeah. Is there any actual experiment? Since I think your code is more complex than
we set the identical model in OpenFOAM and console, and we setting the various operating conditions such as constant current discharge and constant current charge and discharge weight charge dynamic conditions. And we compare the different fields such as the concentration and the current field with console. This is the comparison results with console.
Another question is about the mesh size. You mentioned there are going to be like a million mesh cells within nanometers. Is there any quantum effects that we need to consider, or the classic Ficker law is still holding this scale?
You mean the mesh quantity? Mesh size.
This scale, do we need to consider any quantum effects?
Yes, specifically we have two-dimensional. One is microscopic scale, and the second is macro scale. In the electrolyte thickness, this scale we use the mesh quantity is not refined by the micro scale because this scale doesn't need some complex field quantities. So we use different meshes.
It's still large enough for the Ficker's law, classic laws.
Yeah.
Yeah, I'm conscious of time. I think that thanks all the speakers again for the excellent talk. And also, I think that